Welcome to this explainer. Let's dive straight into the wild, fascinating world of advanced composite materials. If you've ever looked at a modern aircraft or a high-performance car and wondered exactly how engineers build structures that are incredibly lightweight but still massively strong, well, you're in the right place. Today, we're going to completely unpack how these materials work, from the practical manufacturing methods on the factory floor, all the way down to the microscopic properties that hold them together.
To kick things off, let's talk about what a composite actually is. Basically, it's the creation of a super material. When we combine two or more materials on a macroscopic scale, like taking incredibly stiff carbon fibers and embedding them inside a really tough polymer matrix, we form a highly useful third material. And here's the best part. This new material takes on the absolute best qualities of its individual ingredients. When it's designed right, it unlocks properties that neither original piece possessed on its own. It's essentially engineering magic that completely shatters the limits of traditional materials.
So, here is our roadmap for today. We're going to cover the magic of composites, thermosets versus thermoplastics, modern manufacturing methods, automated fiber placement, and finally, we'll tackle the microscopic defect challenge.
All right, part one, the magic of composites.
Moving right along to part two, thermosets versus thermoplastics.
When we talk about the matrix, the actual material that holds all our reinforcing fibers together, we're basically looking at a heavyweight matchup between two chemical families. Their fundamental properties completely dictate how we use them to build things. On one side, we have thermoset composites. These are your legacy choice. They rely on chemical cross-linking. Think of it kind of like baking a cake. Once it's set, it is set permanently. You can't unbake it. But on the other side, we have thermoplastic composites, or TPCs. These are a huge leap forward. They rely on physical solidification and a squeeze flow mechanism. Because they just melt and freeze instead of chemically reacting, they are incredibly flexible for manufacturing. They have an infinite shelf life, and get this, you can actually weld them together. And that flexibility translates to some serious real-world advantages. It's honestly no surprise that the manufacturing world has been aggressively shifting toward TPCs over the last 30 years. They have absolute superpowers when it comes to mechanical and environmental properties. We're talking vastly superior impact resistance, higher fracture toughness, and a much better fatigue life, which is absolutely crucial for high-stress applications like commercial aviation. Plus, they process much faster on the factory floor and offer low fire, smoke, and toxicity values. They really are the materials of the future.
Which brings us to part three, modern manufacturing methods.
So the materials themselves are great, but how do we actually take them and build massive, macroscopic structures? Well, the practical manufacturing landscape is pretty vast. Choosing your method depends entirely on what you want your final product to do. You've got highly automated, continuous processes like pultrusion and filament winding. Then you have liquid composite molding for trickier shapes, and various compression molding techniques using sheet, bulk, or dough molding compounds. Ultimately, every single one of these methods is an intricate balancing act of heat, pressure, and material flow.
To give you a real, concrete idea of how this looks in practice, let's take pultrusion. Picture taking raw, continuous spools of reinforcing fibers and literally pulling them through a resin wet-out station until they are completely soaked. Then, you force them through a series of rigid shaping guides, and finally, drag them through a preheated die where they cure into a hardened shape. It's this relentless, continuous process that takes flimsy little threads and transforms them into incredibly strong, rigid structural beams right before your eyes.
Okay, part four, automated fiber placement, or AFP.
Now, what if you need to build something absolutely massive and highly complex, like an entire aircraft fuselage? That is where automated fiber placement comes in, and it is a total game changer. AFP essentially takes the blazing fast speeds of automated tape laying and mashes it up with the complex geometric capabilities of filament winding. It does this by using multiple, narrow strips of pre-impregnated tape. So instead of trying to force down one wide, stubborn sheet of material, a robotic head precisely steers these tiny, narrow tapes along highly complex contours. It gives us the power to manufacture structurally optimized parts with mind-blowing precision.
And when we pair AFP robotics with those awesome thermoplastic materials we talked about earlier, we get to do something called in situ consolidation. Here's how it works. Step 1, the robot precisely places the narrow thermoplastic tape. Step 2, right as it's going down, a hot gas torch blasts the material with extreme heat to melt it. And step 3, a compaction roller trailing right behind instantly presses the tape down, solidifying it on the spot. The placement and the hardening happen in one single, incredibly streamlined robotic motion. No need to bake the whole thing in a massive curing oven later. And finally, part 5, the microscopic defect challenge. So with all this advanced automation, massive robotic force, and high-tech material, what could possibly go wrong? Well, the biggest challenge we face is actually tiny. Literally. Take a look at this number, 35 micrometers. For context, a single human hair is about 70 micrometers thick. Studies on commercial carbon fiber PEEK tapes show that 35 micrometers is the average surface roughness of the tape right off the spool. Now, that might sound like absolutely nothing, but remember, the entire tape is only about 150 micrometers thick to begin with. That means on a relative scale, the surface of that tape is covered in massive microscopic mountains and valleys. And that robotic compaction roller has to perfectly crush and flatten all of them in a fraction of a second.
And honestly, the surface is just the beginning of our problems. Even the absolute premium, high-performance thermoplastic tapes show up to the factory with an initial internal void content of 5 to 10%. That means 5 to 10% of the material's actual volume is just trapped microscopic air bubbles. So the battle against manufacturing defects doesn't just happen on the factory floor, it literally starts before the material even enters the machine.
To really put this into perspective, look at this cross-section of an actual commercial tape. See all those dark spots scattered around? Those are the voids. Notice how chaotic they are? They aren't uniform. They're different sizes, scattered totally randomly across the width of the tape. When that AFP robot is flying over the part, its compaction roller has the immense responsibility of generating enough raw pressure to squeeze out or completely collapse every single one of those dark spots in an instant.
So why is it so incredibly hard to just squeeze that air out? Well, check out the microscopic zoom on the right here. These are voids that actually survive the robotic compaction process. You can see tiny air pockets surrounded by 4 or 5 carbon fibers that are physically locked together. These fiber-rich areas act like microscopic structural shields. They bear the full brunt of the roller's pressure, creating this tiny protective cage that completely insulates the air bubble, preventing it from ever being compressed out. And we have to care deeply about these microscopic air pockets because they totally dictate the structural integrity of the final product. High void content is directly and inversely correlated with a part's strength. If we leave these uncollapsed bubbles sitting inside an aircraft wing or a load-bearing beam, the fatigue life plummets, the shear strength weakens, and the flexural strength drops. A microscopic flaw literally has the power to bring down a macroscopic giant.
Mastering advanced composites is this constant, fascinating tightrope walk between applying massive, heavy robotic forces and understanding incredibly intricate microscopic physics. And it leaves us with a really provocative question as we look toward the future of manufacturing. If a microscopic pocket of trapped air can compromise our most advanced macroscopic structures, how will the next generation of automation, sensors, and perhaps even AI learn to adapt in real time to solve the void problem of tomorrow? Thanks for joining me for this explainer. Keep wondering, keep learning, and I'll catch you next time.